explaining what artificial gravity is and the methods that can be used to create it. Now, for starters, artificial gravity is basically gravity created through unnatural means. If you don't know what gravity is, it's the force of every particle in the universe attracting every other particle. Now, to create artificial gravity, there are at least two methods you can use: rotation or electromagnetism. Let's start with the natural way to create gravity: mass. Mass naturally creates gravity through interactions with the likely existing entities it moves on. The Earth's mass and the gravity being created by it is what keeps you from floating off into space. There's also an equation for gravity which we'll come into use later in this presentation. The equation is g times m1 times m2 over r squared. M1 and m2 are the masses, are the two masses, and r is the radius or distance between the two masses. Finally, g is the gravitational constant at 6.67 times 10 to the power of negative 11. However, the radius of the Earth is 6.378 times 10 to the power of 6 meters. The mass of Earth is 5.972 times 10 to the power of 24 kilograms. Pretty large, right? However, there is a large problem with this method that makes it pretty much impossible to be used. Now, unless you're 5, you know that the generated gravity is similar to Earth's using just mass would require another planet. And we don't have the technology needed to move a planet, and even if we did, the only planet close to us is Venus. And if we try to use that to cancel out Earth gravity, the sheer force of gravitational attraction would destroy the Earth and us along with it, along with Venus itself. Now, for the other methods, we haven't covered them, so let's check out rotation. Rotation uses centrifugal force to simulate the feeling of gravity. It works like this. You're on a wheel that's spinning. Since you're in the wheel and therefore touching it, you're moving with it, meaning it's pulling you towards the wheel, or the wheel is pulling you toward the outside of it. This can be achieved in space as well, and you need a circle-shaped space station, and then you just need to rotate it at a certain speed. This can actually be achieved here on Earth. Some amusement parks, there are rides, where you and everyone line up on a wall and spin around in a cylindrical building. You're also strapped on the wall, by the way. Once the wall you are on is spinning fast enough, the straps are removed, and you don't fall. You're actually being attracted to the wall. Yep. So you can use this to walk on. So there are also equations for centrifugal force too. So you can use this. Can you use this to walk on walls like Spider-Man? Well, unfortunately, no. There's several elements of the rotation method. One of them is that it's rather limited in the sense that you can't walk on walls or use it to cancel out gravity and levitate. The biggest problem is that if you jump, then the rotating structure you're on is no longer pulling you, so you'll go flying off with the same direction and speed as when you're on the structure. So will you ever be able to walk on walls without using rotation to levitate? Well, there is one more candidate that's the most promising. There's some typos over there, don't mind. It's fine. Electromagnetism. Electromagnetic force is force created by like and opposite charges. Charges are measured in coulombs, and coulombs create force, measured in newtons. But how do you get coulombs? Well, coulombs are created by electrons. So to add charge to an object, you have to take away an electron, and to remove charge from an object, you'd have to add one. You better get ready, because it's going to be a bit of a long lecture. Okay. So how many coulombs does an electron have? Well, electrons have a charge of negative 1.6021765 times 10 to the power of negative 19 coulombs. As for atoms, they're electrically neutral, meaning they have no charge. There are many ways to add and remove a charge from an atom. Electromagnetic force is one of the four fundamental forces in nature, with gravity being the weakest and the strong force being the strongest. How do we know how much stronger? This is why I didn't do that. How do we know how much stronger electromagnetic force is from gravitational force? Well, they both have constants in them, G and K. G is 6.67 times 10 to the power of negative 11, and meanwhile K is 8.87, I believe, or 8.67 times 8.99 times 10 to the power of 9, which basically means that K is 10 to the power of 20 times larger than G. Now, positive charge comes from protons. They have the same amount of charge as electrons, just positive instead of negative. Now, first let's talk about some of the issues of this method. First off, you can't give an atom as much positive charge as you want since it has a limited number of protons. The only way to add protons to an atom is through nuclear fusion, which would create an explosion on par with a nuclear blast. Same thing with nuclear fission. Or taking protons away from an atom, as the only way to do so is split it apart. You also can't expect to add a bunch of electrons to one atom on you, and take away a bunch of electrons on a material, say, for instance, away from you, and expect to be attracted to it. But there is still a way for you to use electromagnetism for artificial gravity and levitation, which I call attraction or repulsion. Now, you told me this before, Trimsy. How group attraction or repulsion works is simple. Say you have many atoms that have one charge added in another group that has instead charge taken away. Since there are multiple atoms, the force of attraction is much greater. For now, we'll call this group attraction or repulsion, or GAR. Which is a bit of an odd name, but it's still a name. Now imagine that there are two people. One of them has a charge taken away from all their atoms. The other recently have a charge added to all their atoms. There are a total of 7 times 10 to the power of 27 atoms in the human body. You get the picture. In order to use GAR, we need atoms, for starters.
Yep.
And we also need to add and take away charge. We'll also need to make a suit in order to attract our entire body towards an opposite charge. The first question is, what atom, element, or material can we use to create this suit along with artificial gravity? You might think that choosing an element with a lot of protons and electrons would be a good idea. But what you should know is that the more protons and electrons an atom has, the more dense and heavier it is. For example, let's look at tungsten. It has lots of protons and electrons, but it's one of the heaviest elements ever discovered. So it'd be like wearing a motorcycle.
Interesting.
Yeah. So I know that we need a material that's fairly light and has enough protons and electrons, so what element can we use? Well, first let's look at some of the dangers that are caused by electromagnetism. One thing you should know is that attraction between opposite charges can create lightning. Lightning, as you should know, is very powerful, containing a million volts of electricity, more than enough to kill anything. And it's been in for starting fires too, so how and where can we find an element or material to solve these problems? Well, first off, to solve the problem of death by lightning, we need a material called rubber. You may have already heard of rubber. Rubber cancels out electric current, which means it prevents you from being affected by lightning. So we solved the problem of death by lightning. What about burning alive from fires started by lightning? So in order to prevent us from dying in a fire, we need a flame-retardant material, or a flame-resistant one. Flame-retardant materials are materials that cannot be lit on fire. For now, we can just call them FRNs. You can find websites for flame-resistant clothing online. A known maker of flame-resistant clothing is called Carhartt, which is a bit odd. However, now we have the materials we need to prevent fires caused by lightning. Now that we have our materials, I should have added this there, how should we design the suit? Now that we have the materials we need, we can start designing our artificial or anti-gravity electro suit. The suit should have 2 or 3 layers. The first layer will be made of fire-resistant clothing or material to prevent any fires from being started by the lightning produced by electromagnetic force. Now the second or middle layer may be an optional layer. This layer should be made of strong material. With the rubber and anti-fire, the materials are strong to support your body weight, as the force of attraction will be applied to them, not your body itself. The first layer, the last layer, will be made out of rubber in order to cancel out the electricity made by electromagnetic force. It should be so covering your entire body, or cover at least 80% of it. You know, seems to be a pretty good idea.
Yeah.
Now that we have our suit, another question remains: what will we be attracting ourselves to? Electromagnetic panels. What we need to attract the suit towards need to be something portable and light, so let's try to go with the panel. But this panel will also need to be able to stick any surface in order to create the feeling of artificial gravity. So we will need to use an adhesive of some sort, like, well, we can't use tapes, maybe rubber or glue, so, or maybe glue of some sort.
Or you could even like screw it in permanently to wherever you
there is
need
that.
it. Yeah.
This panel should also be large enough for you to step on it, so it should be about 2 feet by 2 feet. Fairly large, or it could just be, 6 feet by 6 feet.
Mm-hmm. Sure.
It would have to be designed, it would have to be made in a style similar to the suit we designed. 2 to 3 layers of rubber and flame-resistant materials, and it would be a good idea to add in a durable, preferably flame-resistant layer of material as well. There are still more questions and dangers, however. The other problem is that if you double the distance to the panel you're being attracted to, the force pulling on you will be quartered, or pushing on you, meaning it will be 1/4 as strong as it was when you were at the regular distance. This works the other way around as well, meaning you can end up flying at the panel, or the panel can end up flying at you. That's super fast.
Yes.
It's mega idea. Yeah, retreating to die due to the sheer velocity and kinetic energy of yourself and the panel, unfortunately. This works for repulsive force as well. Only you and the panel flying away from each other at like super high speed. This means we have to be careful when adding and taking away charge from our panel and suit. But if we get the right amount of charge and maintain our distance, we will have achieved the goal of levitation and more. Now, since we know how to make our suit and what to make our suit with, along with our panel, more panels, we have to know 2 things. How do we add charge to an atom, and how do we remove it as well? First off, we can add charge using electrostatic induction. It's the same as polarization, only it's talked about in the next slide. But this may be our only way to positively charge our suit or panel. If we were to use a negatively charged object to separate the electrons from the atoms on opposite sides, basically you hold it, there's a sphere here, you hold a negatively charged atom, the protons go that way, the protons go this way toward your electrically charged, negatively charged atom, and the electrons go this way. Now, basically we can use friction to remove it, making our suit or panel positively charged, or we can just simply hold an electrically neutral object next to it, next to the site that's containing the electrons that are being repulsed by our object, which electrically charges our suit as well. Now, since this is pretty much our only way, we could either use use electrostatic induction to induce a positive charge on an object, or we try to create atomic or molecular scissors of some kind that can pluck atoms from from atoms. Electrons from atoms.
Yes, that'd be.
I prefer electrostatic induction. So we have our pretty much only way to add positive charge. But how do we remove charge from an object? To remove charge, we can use something like friction. Friction works by rubbing an object against the surface. The electrons rub off the atoms on the surface and onto the object rubbing against the surface. To simplify this, I basically rub my hand on this table and I get negative charge. Though rubbing our suit against an object for who knows how long isn't very time efficient, so we can speed up this process by using a Van de Graaff generator. A Van de Graaff generator is an electric generator that gathers electrons onto a hollow sphere, which makes removing charge easy. All we need to do is simply hold our suit or panel close to the Van de Graaff generator and the charge will be removed. We can use polarization, which is simply holding an electrically neutral object, and we talked about which is the same as electrostatic induction, before. So this isn't really the best way to give ourselves negative charge, so let's go to positive charge. Next up. Oh yeah, we also need to know how to keep our charge. We can use insulators, or electrical insulators to be more precise, that are materials that have electric charges that do not flow freely, meaning it keeps its charge without wear and tear from everyday conditions. Materials that are electrical insulators are glass, paper, and Teflon. Teflon is the most promising one since using glass in this, it will make it very difficult for you to move, and paper isn't exactly comfortable. It has the potential to set on fire. So yeah, Teflon would be our best pick. That's how I use Teflon in experiments too. Now, we could use Teflon for our suit to keep our charge, or we could just not use it, because there's a problem with insulators and that. Since they keep their charge, it may be hard to change it. But it's possible to use this material, but actually rubber's an insulator too, so we could just simply use that in our suit instead of the Teflon then.
Yes.
Now that we've covered insulators, let's find out how much charge we need for levitation and walking on walls. For levitation, we can evenly distribute charge along our electro suit without worry. For this, we'll use Coulomb's law and calculate the charge necessary for levitation. But first, we need to know how much force the Earth is pulling on us with this, using that equation mentioned earlier in the mass method. Yeah, how much force pulling on us with the equation. Yeah, you know what I mean.
Yep. Gotcha.
Let's start off by converting weight into kilograms. 1 kilogram is about 2.2062 pounds. We're about 160 pounds. So 115 divided by 2.2 equals basically about 52.16 or 53 kilograms. Now then, we'll use the mass of the Earth and the radius of it as the other two variables in our equations. The result is that the Earth pulls on you with 110.756 newtons. In order to counter this, I'm going to have to enter in a bunch of calculations that are mainly guesses, but they should be fairly accurate guesses, and we'll also be using Coulomb's law. Since I didn't discuss this earlier, I'll discuss it now. Coulomb's law is an equation. The equation is shown above. K in the equation is 8.98 times 10 to the power of 9, much larger than G. The Q's are 1 and 2 are the charges, and R is the radius. After the pretty accurate guessing, the amount of charge required to counter gravity at 1 meter is 3.2 times 10 to the power of plus number to the power of negative 4 as a bit of an issue, and 1.6 times 10 to the power of negative 4. Although the result is 459.776 newtons. The distance is at 1 meter, so if you were to simply gently lower yourself onto the panel, the gravity will be pulling on you, and so will the panel be pushing against you.
Sure.
So it will allow you to levitate, since
As you get closer to the strawberry.
Yep.
Yeah.
This equation will be a little different. First of all, being attracted to the panel. We're being attracted to the panel, so we'll need to shift like whatever. Well, so we'll need to lower our charge as our feet will be extremely close to the panel. We have to unequally distribute our charge too, meaning anyway, now how much charge will our feet and power be segment to each other? Well, the electromagnetic panel will need a positive or negative charge of 1.67 to the power of negative 7 coulombs. And so we'll have to have an opposite charge of 3.2 times 10 to the power of negative 7. Of course, the suit and electromagnetic panel will be extremely close to each other, increasing at 0.21 meters since touching it. To create this effect and the charge will probably be equally distributed throughout, could be equally distributed throughout the suit. So it might be more like crawling on walls than walking on walls.
Yes.
That's my mind.
Yeah.
In order to actually walk on walls without feeling like you're looking at Jupiter, we'll need some sort of intelligent computer system integrated into the suit. This system will have to monitor the distance and charge of our suit and or the electromagnetic panel. And whenever the distance changes, the computer will have to automatically alter the charge quickly in order to keep the force exerted on the suit the same. Of course, this is in the realm of theoretical science. A computer that monitors and changes charge according to changes in distance is a bit of a possibility. But can we ever use electromagnetism less pseudo and not worrying about frying ourselves like a chicken? well, we could do this, but what I'm about to talk about is basically in the realm of theoretical science fiction, whether it might be possible. My idea for using electromagnetism without a suit would be to use a swarm of nanobots to add or remove charge from the surface. This means you can control lightning like Thor. Oh,
okay.
The nanobot swarm would then be controlled through a neural implant that could send signals to the swarm.
Okay.
They could also use nanojets when it comes to propulsion and stuff. We also shouldn't forget the danger of lightning, as you would have to swarm with you until the implant is removed. solve the issue. The answer lies in one person. This person is named Ma Xianggang, or whatever that is. I'm not that guy pronouncing it. This man can be shocked with as much as 200 volts of electricity, I believe, and take no damage. He has actually said that electricity gives him energy. Now, to solve the issue of movement, the nanobots could simply use wind or nanojets. Just tiny, you know what jets are, tiny little jetpack things that push them along and control the points of Torres. If we could use this ability, if we could use Ma's ability, kind of weird, then we could use rather high charge and take little damage. This effectively gives him some control over lightning and gravity. We could likely raise the limit of electricity in the future. As I said before, this is purely theoretical, and perhaps it is possible. But it was said that the temperature could not go or get any colder than absolute zero, and a group of scientists went ahead and did it. Reaching negative Kelvin, by the way. This goes to show that perhaps anything is possible.
Very good.
For centuries, man has wondered if we'll ever be able to fly or levitate, or if we could ever create gravity in space. These questions have now been answered. The technology and methods used to create mentioned in the slide will likely be used in the future. For future spacecraft missions. And technology is advancing as well, so the subject of the previous slide could happen. I am Chance Torres. Thank you for watching this presentation.